Number 74, we have a capacitor of capacitance C is connected to a battery of EMF E at t is equal to 0 through a resistance R. We need to find the maximum rate at which the energy is stored in the capacitor. Maximum rate at which the energy is stored in the capacitor, and when does the rate has its maximum value. So we will try to find the energy stored in the capacitor, then we will find the rate at which the energy changes, and then we find the maximum value of that rate of the change. So these are the three things. So let's say we have, this is our question number 74. This is our resistor, this is our capacitor, and we have a battery. You can think of a switch here and then a battery of a given EMF, so let's say E. The capacitor has a capacitance C and this resistor has a value of R. The energy in this capacitor U has a value of half Q square by C. We also write as half CV square because you can write Q as CV, so C square V square, and square and C cancel. So this is also another formula, but we are going to use this one for our purpose. Now this energy, we need to first find the rate of the change of this energy, of storage in this energy, and we know that the Q is given by this Q here is a function of time. Initially, this when we switch is just closed, this battery has voltage E and this capacitor is uncharged. So a charge starts flowing through this resistor to this capacitor, and that charge has a maximum value initially. The current has a maximum value initially, and initially the charge on this capacitor is 0. As more charge accumulate, there is some more capacitance on this capacitor, and because the resistance, the difference in the voltage across this resistor reduces, the current flow in this resistor reduces. So we have a value of Q as Q naught 1 minus e to the power minus t upon RC, and Q naught is the initial charge, final stable charge on this capacitor, which happens when the voltage on this capacitor becomes equal to the voltage of this battery. So we can write this as Q is equal to CV, so C epsilon 1 minus e to the power minus t divided by RC. Now we can substitute this value of Q right over here, so we get U is equal to half, this is C square epsilon square, cancelled by C, we have epsilon square C multiplied by 1 minus e to the power minus t upon RC whole square. Now we need to find the rate at which this energy storage in this capacitor changes. So recall, let's call this rate R, which we say as du by dt, and that will be equal to, this whole thing stays constant. We need to differentiate this whole term with respect to t, so the differentiation will be nx to the power n minus 1, so half CE square multiplied by 2 into 1 minus e to the power minus t upon RC multiplied by differential coefficient of this whole term. So differentiate this sum, we have minus e to the power minus t by RC multiplied by differentiation of this term, which is minus 1 upon RC. So it can be simplified a little bit. Minus minus cancel, this C cancels with this C, so we get R equal to half. Okay, one more thing, this 2 cancels 2, so there is no half here. Epsilon square divided by R, E square divided, we will just call it e, not epsilon, but just for the sake of convenience. 1 minus e to the power minus t divided by rc multiplied by e to the power minus t by rc. So this is the rate of the change of the charge storage on this capacitor. Now we are asked, when does this rate becomes maximum? So to find this maximum, what we need to do is just differentiate it one more time and equate it to 0. dr by dt, that will be equal to this constant term e square by r and its differentiation. First term, just write the first term, 1 minus e to the power minus t by rc multiplied by differential coefficient of the second term, which is e to the power minus t by rc multiplied by differential coefficient of this is minus 1 upon rc, plus second term e to the power minus t by rc multiplied by differential coefficient of the first term, which will be minus e to the power minus t by rc multiplied by differentiation of this term. This is minus t by rc. Now we can simplify it a little bit more. So we have dr by dt is equal to e square by r. E to the power minus t by rc is common in both of them. Okay, and we write it e to the power minus t by rc, and also rc and rc are common. So let's take that out. Divided by rc. Multiplied by, in the inside, rc is gone, this is gone, this is minus 1 minus e to the power minus t by rc, and this is minus minus plus, this is no t here, this is just 1 here. This is minus e plus, minus minus becomes plus, one of the e to the power t by rc and rc are gone, so we have e to the power minus t by rc. And we are interested when this term becomes 0. This term becomes 0 when this whole term becomes 0, which happens when this plus this is 2 times of e to the power minus t by rc minus 1 is equal to 0, or when e to the power minus t by rc is equal to half. So this is the condition when the rate of the change of the energy becomes 0. To find the value of t, we can take the natural logarithm, which is minus t by rc log e to the base e is equal to log 2 to the power minus 1. 1 by 2 is 2 to the power minus 1, which can be written as minus log 2 to the base e. Minus minus cancels. Log e to the base e is 1, so t is equal to rc log 2 to the base e. So that is one part of the question, when does the rate becomes maximum. The second part is, what is that rate? To find this rate, take this value e to the power minus t by rc equal to 1 by 2 and substitute it in this equation, this rate equation. So this term then becomes equal to, if you look at it, r equal to, okay, e to the power minus t by rc is 1 by 2, so this is 1 minus 1 by 2. So e square by r multiplied by 1 minus 1 upon 2 multiplied by e to the power minus t by rc is 1 by 2, so keep it 1 by 2. So this implies r is equal to e square divided by 4r. So let's check its answer here. Question number 74, we have, this is the answer, e square by 4r, e square by 4r. You always want to check your answer. Make sure you have not done any mistake in the calculation.